we'll actually just start a stream.
Yep.
That works. Name of it. Okay, that should be, but I think we are we live?
No, let's see how I can open YouTube over here and see what's going on. Let's see.
I believe we are live in public, so I think we're going. Okay. So, let me go into the, see if we got any viewers. Okay, we got 44 people watching. Cool. Okay, we're making progress.
Okay.
Okay, so let's get started, and people will come in as they come in. First of all, very sorry that the technology didn't work our first try.
It wouldn't be a meeting without a problem with the projector, right?
But it's working now. So, ladies and gentlemen, this is James Douma. Am I pronouncing it right? I think I got it right this time. Oh,
that's right.
I'm gonna get my microphone where it needs to be. So, I saw AI
I'm
Day.
getting room audio from you, by the way.
What do you mean by that?
So you kind of sound like you're in a room as opposed to on a near field microphone. So I don't know if you have a near field microphone. If you do, then you're not using it right now. It sounds like I'm hearing you from maybe your laptop speaker or microphone or something.
Oh, I think I know what you're talking about. Okay, give me a second. I think that's probably what you're hearing.
Mm-hmm.
And I think...
Yeah, as long as it's okay I can hear you fine. I just... some people are very picky about audio.
Does it sound better now?
Yeah.
Okay.
A little too loud, but now you're on the near field mic.
Okay, let me just check our volumes here.
Okay, that sounds good.
So can you give me a count? 1, 2, 3?
1, 2, 3. 3, 4, 5, 6, 7, 8, 9.
1, 2, 3. Okay, I think we're good. Hello, testing 1, 2, 3. Okay, it looks like we're good. Okay, so we've got an audience. We're starting good. Who's too loud? Tesla Sweden says somebody's too loud. Am I too loud or is James too loud?
Well, I'm not talking.
No, I mean, I'm looking. I think I'm still too loud.
Yeah, you sound pretty loud to me.
Hello, testing 1, 2, 3. I'm turning down the gain on the mic, which should affect both you and them. Okay. All right, let's go ahead. So, James Douma, you saw AI Day. Initially, just your general impressions. What did you think of Tesla AI Day? What got you excited? What are you thinking about?
What got me excited? What didn't get me excited? Everything they presented was really interesting. They, man, what got me excited? Just wow, they're really doing a lot. I think it's easy. It's easy to think that there's not much going on when you can't see behind the curtain. And I think that's probably a bias that everybody falls prey to. And despite the fact that I've tried hard not to fall prey to that bias, right? Looking at what comes out of the car, watching the car develop over time, I had sort of deluded myself into the sense that I sort of understood the scale of the things they were doing behind the scene. And then AI Day basically showed me that I was wrong about that. They're operating on a much bigger scale. And they're operating at a bigger scale, they have bigger ambitions. And the dynamics of the effort is changing relative to how it was in the past. I mean, the first part of the talk where Andre came out and he talked about the details of how they're implementing the networks. Well, I looked at earlier versions of the network. So like what they're showing right now is much more sophisticated, much more ambitious, much more complex than what was in the car 12 months ago, 24 months. I mean, 24 months ago, the stuff was really simple, and the network that Andre described. Now I'm just using this as one example of what's going on, but the network that Andre described is just like it's on a whole different level than the stuff that I was looking at a year ago. Say,
what do you mean by the network? What is the network?
So neural networks, they're composed of neurons, right? And they're a network, so you tie the neurons together in some kind of pattern.
Let me just stop here a second. Are we talking about the chip in the car, or are we talking about the training computer when you talk about the network?
This is the software that runs on the car Okay, so
Yes.
when I started looking at the technology that Tesla was doing, one of my initial, I mean, initially I got the car and I drove it around, and I spent a bunch of time thinking about like, how do they do this? How do they do that? Look at what the state of the art is. Try to understand the techniques that they're using. And then at one point, I was somebody who got into the car and pulled the software out, started feeding me stuff that he was finding that was running in the car. So the thing that I was mostly interested in is what were they doing with the neural networks to achieve what they were achieving in the car at that point in time. And so I was looking at the neural networks. So when I talk about the neural networks, I'm talking about the architecture of the network that they're using. And that's a software that's an aspect of the software in the car. So you could think of the neural network as a it's a block diagram with a lot of blocks and a lot of lines running between them. And the shape of that overall block diagram, that's what I call the network architecture. Okay, the network architecture, it's in a sense, it's kind of like a fingerprint. If you've looked at a lot of these things, you can look at a network architecture and you can get a sense of what they're trying to accomplish and what the bounds are and what they're doing. And you can look at what other people have done to get a sense of like what a particular network is capable of, what kind of resources it takes to run, what kind of resources it takes to train, how much data it takes to train, what things it's synthesizing, how much abstraction it's trying to develop as it generates these outputs, all that kind of stuff. You can get broad ideas of it. You can't really get too far down into the weeds, but the alternative, if the alternative is buying the car and driving it around and just wondering about what's inside there, it's a lot of data, right?
Well, let me ask you this, because somebody just asked this in the chat, and I have this question written down. Andre said at one point in the Q&A, he said, in the limit, the neural net has enough parameters to potentially remember Earth. Yeah. What did he mean? Is that Dojo, or is that the neural net in the car?
That's a neural network in the car.
So what does it mean?
That what they do, just to be clear, right? They're in the process of developing a neural network that can run on the car and do the job they want it to do. To create this neural network, they put it in a data center and they train it on a ton of data. And then once they've got it trained up, they push it out to the car. And then the car runs it on the FSD computer that's in the car. So it's the same neural network that's in the data center is in the car, because they make it in the data center and then they put it in the car where it does its job. Okay, so I'm talking about the neural network. That's the neural network I'm talking about broadly. Now, they use other neural networks for other things. In the process of training the neural network in the data center, they need to build this large corpus of data. And to build and label this large corpus of data, they have all of these tools that they've developed that they use in the back room to essentially automate various elements of the process of building that corpus. So those are other neural networks. But when you hear me use the term the neural network, I will be talking about the main one that they train for the purpose of putting in the car, for the purpose of driving the car.
So what does it mean to remember Earth?
To remember, so this was in response to Elon had made a comment. The context for the statement that Andre made was Elon had made a comment where like, oh yeah, it's like ESP. Sometimes it seems like the car is just, it knows things it can't see. And Andre was saying, yeah, occasionally we'll see something like that. And is that in the training set? So if something is in the training set, then you showed it to the neural network while you were training it. And so in principle, the network can just remember it. It doesn't have to figure out the answer in this situation. So like, for instance, the car's driving along and there's some obstacle, right? And it can't see on the other side of the obstacle. Maybe it's a wall, maybe it's a bus or something like that. So the neural network in the bird's eye view network, it is trying to predict what's around the car out to a certain radius in all directions, as if you were looking down from the top. So if there's, for instance, a wall next to the car, the neural network in the car, it has to guess what's on the other side of that wall. It doesn't know because it can't see it, right? So one of the things that the BevNets do is they fill in those blank spaces with their best guess about what's going on. And Elon was pointing out that as the network gets better, eventually the things it guesses are uncannily accurate. And that was why he used the term ESP to describe it. It's like, how does it know what's on the other side of this wall? And Andre had said, yeah, occasionally we see that, and we wonder if that example is in the training set. Because if it's in the training set, then the neural network does know what's on the other side of the wall, because it was in the data that the neural network was trained on.
Yeah.
Okay, so this is in a sense, this is kind of a flaw in a neural network. If you're training a neural network and it's remembering the training data, you don't want it remembering the training data in the general case. What you want it to do is understand the pattern of all the training examples collectively so that it generalizes and it makes good guesses because it sees the pattern in all the examples it's seen. So it can guess what's on the other side of a wall because, it knows from previous examples that, if one end of the wall is this and the other end of the wall is that, and I'm on this kind of street and the weather is like this and there are this many people on the street, then this will be on the other side of the wall. You want it to figure that out.
Is it really remembering things, or is it just reacting to images and the training? Is remembering the right term?
So remembering is a failure mode in a sense in training a neural network. If you're training a neural network and mainly what it's doing is memorizing the training data.
Right.
That's not what you want it to do. You want it to generalize from the training data. You want to use it to take the training data as examples of what the world is like, so it makes good guesses. So the problem with memorizing data is you get a failure mode in a neural network. It's called overfitting. So when the process of training a neural network, you build this network and you have all of these examples where here's an input and this is the output I want you to generate for me. And the process of training is you give it an input and then it guesses at what the output is. And then you say, no, this was the real output. And the difference between what it should have said in the ideal case and what it did say is an error signal that you feed back to the network. And when you feed it back to the network during training, it slightly adjusts all the parameters in the network to be more like the correct answer. And if you do this with enough examples, what happens is it gets pretty good at predicting things. So for instance, you can show it a picture and you can say, is this a cat or a dog, right? Yeah. The canonical example. And you show it lots of pictures of cats and lots of pictures of dogs. And each time it says it gets it wrong, you feed an error signal back to make it slightly more right. And after enough examples, it'll get pretty good at telling you whether it's a cat or a dog. So they're doing this on a much bigger scale in the neural network they have. But say you're showing it pictures of cats and dogs, and it's memorizing all the pictures, right? So you've got 1,000 pictures of cats and 1,000 pictures of dogs, and it's perfectly good. Every time you show it one of the pictures it's seen, it says, yeah, that was a cat, that was a dog. The problem is this becomes weak because what you want is when you show it a new picture of a cat it's never seen before, you want it to say cat. And if it's just remembering, to the extent that it's just remembering the pictures it has, it may lose the ability to generalize. So when you show it something it hasn't seen before, it'll fail. So as a general rule, when you're training a neural network and you see it's memorizing the data, you're overfitting. There's various things that you do that can cause it to overfit or underfit or generalize correctly and whatnot. And so it's a warning sign when you see the network start to do that. But then Andre points out, well, on the other hand, if we have enough parameters, it can just remember the whole world, right? So if you have a big enough neural network, remembering everything isn't necessarily a flaw, right?
But that doesn't make sense to me. I mean, the number of if we're remembering if we're doing a point cloud for the Earth at centimeter scale, the number of points is a heck of a lot larger than the memory capacity of the chip or the size of the chip.
Right now, yeah. But Andre said in the limit, the neural network can remember the world. So right now, the neural networks have on the order of they have 35 million parameters. The networks I was looking at that they had in the car, I don't know, maybe the first version of FSD, there were like 35 million parameters in an individual network. And then they might have had, I think I saw that they had like 100 neural networks that sort of, and this is a big overall function that's broken down into blocks where each block runs separately. And I'm calling each one of those a network right now. Yeah. The overall network is kind of the composite of all of these things working together to generate the function of driving.
So 3.5 billion. 35 million times 100, no, 3.5 billion.
35 million parameter kind of scale. But the thing is, we know from other neural network experiments that you can build billion parameter. In fact, GPT-3 is 175 billion parameters. And that was how they got to that crazy capability that they have. You could build 1 trillion parameters. You could build 10 trillion parameter networks, right? I mean, there's no upper scale. These things just scale basically without limit. So, how many points would it take to remember the Earth, to just store the world in the neural network? And so this is kind of a quip that Andre's making, that like, eventually the networks will be big enough and they can just remember the whole world. But it's not a serious comment about what they're doing today.
Okay. All right. So I want to turn to, let me actually, one question about Tesla Bot. We may come to Tesla Bot later, but one question, because it came from one of my moderators, my chat moderators, was for the Tesla Bot. The way I understand it, shadow mode in a car is the human is driving the car, and the FSD is predicting what's going to happen and then learning from what actually happens as a human is driving the car. And the question which other people have asked is, how does shadow mode work in a Tesla Bot? And Jim suggested, what if a Tesla Bot was teleoperated, and then the software learns from the way the human operates the bot? Do you think that's going to be how Tesla Bot is going to learn initially, or will be learned in simulation, or how are they going to train the bot in the beginning?
Okay, so your understanding of shadow mode is a little off. So let me correct that.
Sure.
Shadow mode. You can run as many neural networks in the car as you have capacity to run. And say, for instance, that it only takes 20% of the car's capacity to run the neural network that it needs to drive the car. So a thing that you can do with that extra capacity is you can put test networks in there, right? You can say, well, this is a thing we're thinking about doing, but we don't know if it'll work in the real world. Let's put it on some cars and run it and see how it goes. Well, you can't let it drive the car because it's a test network, right? But what you can do is you can watch how it behaves. Like, for instance, you could compare its output. Like, if the thing you're testing does the same thing as some other thing that's in the car that's actually driving the car, and you think it would be an improvement, or at least you hope that it's not regressing, you run those two networks together, and one of them, the one that how it's performing, that's driving the car, it generates a set of outputs. So you can run the other one in shadow mode because it's there and it's operating. But the reason it's in the shadow is because you can't tell from the behavior of the vehicle that it's there. But Tesla can record its outputs, compare it to the running network. Okay, so shadow mode, that is the running of a neural network for the purposes of evaluating the network, not for the purpose of driving the car. There are many different ways you can use this that could be useful. You could compare the shadow network's output to another neural network that is working, or that how well it's working, and you could look to ask the question: is it better? Is it working better than the network that's in the car? Like, is this a reasonable approach? Another thing you can do is you can compare the network, and this is what I believe your question was based on, is you can compare a shadow network's output to what the human is doing. Like, say you're trying to model what the human does. Like, the human is the neural network that's maybe, in the case where the human's actually driving the car, you could run a network in shadow mode, and you could try to predict what the human's going to do. What lane is he going to take? Is he going to turn left here? Is he going to turn right here? Is he going to stop at this line, or is he going to stop up there, or she?
Well, just really quick.
So
you're not only predicting what the human's going to do, you're also predicting everything else that's going to happen at the same time.
Depends on the network, right? But you can talk about the neural network that's in the car as a single unit because it can kind of be thought of that way. But you can also think of it as decomposed into different networks that have different functions that kind of work in this big block diagram and pass things between each other. So depending, the thing that's running in shadow mode isn't necessarily a full up driving network, right? It might be just, for instance, when they were doing the push to get radar out of the cars and switch over to just using vision, what they had radar in the cars, right? They're driving along. And so in the first step of that effort, what they did was they were like, let's make a neural network that tries to predict what the radar will say. Right? So the cars are driving around and the radar is saying, this is how fast the car ahead of me is going, and this is how far away it is. And you have a neural network that's just taking the same picture from the camera, and it's trying to say the same thing. And so that network can run in shadow mode on the car, where what you're doing is you're comparing it to what the radar is actually saying out in the world. So that's That's a a pseudo radar.
Pseudo radar, pseudo lidar. Yeah, pseudo radar. Yeah.
It's a pseudo radar neural network that you're running maybe on customer cars and maybe on test cars out in the real world, so that you get lots and lots of examples in the real world about how well it works. So what you can do is you can modify that network over time to see how your modifications work. Like, oh, we trained up a new one. Let's put it out there. Is it still phantom braking at bridges? Yeah. Or, does it, is it still phantom braking because it erroneously thinks the truck is, in the road when it's off the road? Yeah. Stuff like that, right? So those are all examples of shadow mode. But shadow mode is this very broad capacity that you can use in various ways to solve different kinds of problems. It's just there because of a couple of things. Tesla can push networks to the car whenever they want to. So they can update the code. They're not like Ford, where you got to take it to the dealer and they got to put your car, in the garage and take it from you for a day and then update the software. They can push new software every night if they want. Yeah. They can push parameters probably even faster than they can push. So there are situations where they might have a parameter that controls some function in the car. For instance, like how fast do we want the car to accelerate? That doesn't necessarily need to be something that's determined by the neural network. There can be a parameter that goes into the system as a whole, and they can push. And actually, when you do this, because you've got a whole fleet of cars, you might say, well, this value could be 0 or it could be 1, and we don't know what the right value is in between these two. So what you do is you send 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8 out to, 1,000 customers in parallel, and you see which ones have the best experience, right? So like a week later, with that one push, you can gather all that data and you can say 0.72, that's the right number, right? And then you've answered that question. That's another example of, shadow mode potentially, right? If the function that you're testing isn't driving the car and it's not the customer doesn't know, it's not affecting the drive itself, that's shadow mode, right? It's a neural network which is running in the car to help Tesla develop neural networks and not to drive the car at that particular moment.
So turning to the question then, I want to go to Dojo next, but I just want to get Jim's question there. If you have you have this new Tesla bot and it doesn't know anything yet, maybe it's able to learn something from what the cars have learned, but maybe you have to train it from scratch because it's got different cameras. It has a different perspective on the world. The cameras are at different heights. Probably doesn't have 8 cameras. It might have 4 cameras. I don't know. Would it make sense to train it by having humans teleoperate it and have the software / hardware / neural network / whatever learn from how the human operates it? Or is that probably a dumb way to train the bot?
It's probably not how you want to go. There may be particular things that are problematic to do with other more efficient techniques for whatever reason. And so maybe in that situation, you would have a robot. People have built robots in the past where what you do is you don't necessarily have a person teleoperate it, but you might have someone come in and manipulate it sort of directly, or just do a demonstration, right? People have tried training robots. There's some really amazing work where a robot learns to do stuff by watching YouTube videos of people in the kitchen. Like, how do you chop a carrot? So you watch a bunch of YouTube videos of that kind of stuff, and the robot tries to mimic the action. So that's a way that you can provide instruction to a machine about how to go about some kind of process without having to get into actually trying to. Because teleoperating a robot is really hard. They've got a lot of degrees of freedom, so it's not something you can do with a joystick.
I almost think you would maybe you would wear a suit that has all these sensors. Then you would move it.
And people do that too. Yeah. There's a great body of research. I love this stuff. This is a guy named Jason Peng does this at University of Ontario, I think. Anyway, he started out working on this problem, which was. Essentially, it was about doing motion capture, and they were using neural networks to just, when you're doing motion capture for a movie or something, and you have a human put on a black suit and it's got markings and stuff, and they move around in front of cameras, or you have something that measures their action, and then you go and then you animate, a dinosaur with it or something, right? Well, it turns out that motion capture frequently the hardware that does the motion capture sensing directly has all kinds of problems, and the data that you get out of the motion capture is really noisy. And so they were just trying to come up with a filter how do we filter motion capture data to make sure that what we are actually trying to animate actually makes sense? Because doing it by hand is really hard. It's kind of like the teleoperated robot thing. So he tried building a neural network model to, I'm going to probably mess up this description of his work some, so I'll apologize in advance to him in case he happens to watch this. But he was trying to build a filter to, kind of sanitize that. And what he ended up coming up with was this really beautiful piece of work where a human using motion capture could go out and do something, and you'd train a neural network model to learn that action. And then he could take a robot in simulation, even one that differed from the human in significant capacity, and you could train it using this reinforcement learning algorithm, and it would learn to mimic that action like really well. So at a time when Google engineers were like, they would have these little robots in simulation that were struggling, just, they'd run really funny with these very unnatural gaits. Jason had these, he had robots in simulation doing spin kicks and backflips and cartwheels and all of this amazing stuff. So yeah, a human wearing a motion capture suit and doing something. I mean, there exist extremely powerful, super effective techniques for just training a robot to do that.
Okay.
Directly from the motion capture data of a human being.
Okay, so I hope we're going to come back to Tesla Bot later, but I honestly, I watched AI Day, and for me, the biggest thing was Dojo. And I don't know how you just sort of start off with what are your general impressions of what you saw about Dojo?
Sasenga desu ne, Tesla. It was super impressive.
Yeah.
Okay, so we got the teaser image from the AI Day invitation. And from the teaser image, that basically gave it away. We knew it was a multi-chip module, and they had these giant die on it. So we knew, about the packaging technology that they were using. What we didn't know about the chip architecture, and we didn't know about the architecture they were going to try to do at the cabinet scale or at the super cabinet scale, the data center scale. I am really, really excited about it. For years now, 3 or 4 years, when I've been complaining that adapting GPUs to this task or trying to add little, instructions to CPUs to do deep learning was not the right way to do it. And the startups in the space right now that build deep learning accelerators, they almost always had an architecture that they were working on before deep learning really took off. So it wasn't a clean sheet design, which is just like, how do we train a neural network, or how do we run a neural network in the real world? So with the FSD computer, Tesla went out and they built a chip in a car for running a neural network, for doing inference. This is what you do when you've got a trained neural network and you're using it to actually do some kind of job. And the FSD computer is a very good implementation of that for the time that they developed it and what the low-hanging fruit was in the application they have. It's a really, really nice implementation of that. For training a neural network, you need a lot more flexibility and sophistication. And that, this D1 chip and the compute node that they have, it's very clearly a completely from scratch piece of silicon that doesn't do anything except train neural networks. And it's going to be much better at that job than any CPU or any GPU or any pre-existing design which has just had training neural networks added to the long list of things it already does. This thing only trains neural networks. That's all it's designed to do. And it's going to be really, really good at it. And it's completely optimized for it. One of the things about training neural networks is because it's matrix math, just on a really big scale, it has a lot of extremely regular structure to the way that the problem works. And if you build an accelerator whose only job is to do that, you can make extremely efficient use of silicon, extremely efficient use of bandwidth, extremely efficient use of power, because there's all kinds of flexibility that you don't need because you're just training. And so, they've designed this compute node and they've designed this chip. And they've designed this fabric for how all of these chips talk to each other, which is just specialized to that. And it's going to be, it's a pretty ambitious project. They're designing the silicon, they're designing all the packaging technology. Getting the network to work between the cabinets, like, this is not easy. Yeah. This is an extremely ambitious, extremely difficult system to develop. And I won't be surprised if it takes them a little while to actually get it working the way that they want it to work. That said, when they get it working, it's really going.
Let's
to
be
rock.
clear. They appear to have one tile working.
Yeah,
they showed a tile doing mini GPT.
So they have first silicon, and they've packaged it, and now they're sorting out the interposer bandwidth interconnections inside their multi-chip module. And I mean, they showed us a picture of this thing sitting on the bench. Right?
Yeah.
It's not in the cabinet.
Right.
It's in a test fixture on a bench. So that's where
that's probably not the final version of the cabinet hardware.
Well, they don't even. I mean, we didn't see cabinet hardware.
No, they had like a couple of black tubes going in for cooling and a couple of power cords coming up underneath. Right. That's probably not how they're going to design the cabinet.
Nope, it's not going to look like that. They've got a lot of stuff to do. Yeah.
Well, what was that bit?
That said, they're moving at Tesla speed, right? This is not your your mother's data center development company, right?
Yeah, that's a question I have for you later about that, but. Tesla speed. Hang on. I'm going to use that later when I talk on a question I have later.
That's I stole that from Sandy Monroe. That's his.
Okay.
So give him credit.
So Elon said it's a quintillion floating point operations per second, enough to simulate a human brain. I think that's the same as an exaflop, right?
Yeah, 10 to the 18 operations per second.
Okay, so first question I have for you is, well, I mean, I think I know the answer to this. I think you and I both know this. What's a flop? Floating point operations per second?
Floating point operation. So it's, if you have a floating point number, numbers can be represented different ways in computers. And the sort of classic scientific calculation is done with floating point numbers because they have high dynamic range. So instead...
No, they're doing integer operations as well. They're not just doing floating point operations, right?
Right. Yeah, the people like to use flops. So for supercomputers are traditionally, they solve scientific problems. And in fact, for a really long time, the scientific problems required like 64-bit floating point, like, double precision floating point. So single precision floating point is 32 bits. Double precision is 64 bits. And double precision floating point was the gold standard because that was what you needed to simulate airflow, to simulate rocket engines, to simulate weather, all that kind of stuff, right? Or you want to do, astrophysics simulations, you're using float. So that was most big iron that was used for scientific computing was really focused on making double precision work. Okay. Subsequently, there have been problems where single precision made was also really important, and they were more optimized for single precision. Well, it's half as many bits. Frequently, you can get 2 or 4 times the speed up if you're only doing 32-bit stuff. But it turns out deep learning is a qualitatively different type of computation when you're training neural networks. They do not need very much precision. And so now we see 32-bit, 16-bit, and even 8-bit floats. Like they have a CFP16 format that they're using in this because that's enough to do the thing. And if, I can do twice as many 8-bit operations in the same silicon as I can do 16-bit operations. I can do 4 times as many as I can do for 32. And you see most of the organizations out there that are making silicon for doing deep learning, you're seeing them add more and more of these deep learning specialized numerical formats to their processor. NVIDIA has been doing it. Intel's been doing it. Everybody who makes silicon is doing this kind of stuff. And Tesla is doing the same thing, except their architecture is really focused at milking these really low precision formats and getting as many of them as you can. So when Tesla talks about a flop here, a floating point operation, they're talking about CFP8 and 16-bit floating point operations. And I believe that the reason that they call that number out is because their atomically useful piece of numerical computation is taking 2 CFP8s, multiplying them together, and accumulating the result into BFP16 format, probably. So, I mean, that's a pretty silicon efficient way to do deep neural network training, which is it's a good trade-off between As you go to lower resolution, the training algorithm gets a little more complicated because it has to keep track of like round off errors and scaling and that kind of stuff. The smaller you go, the more time you have to spend sort of adjusting for these scaling issues. On the other hand, if you use 32-bit floating point numbers, you don't have to worry about any of that stuff at all. It's very easy to write the software, but you're wasting a ton of silicon because most of the minimal operation you need to do is much lower resolution. So Tesla's built a piece of silicon that works at multiple scales, so that you can run an easy, quick, and dirty thing, and you can drop it on the silicon and it'll work and you'll get a result. And if you really want to optimize it because you're going to run this puppy at scale, you can optimize it down to BFP16, and then you can further optimize it down to CFP8. And each one of those steps gets you a lot more performance, but it makes you have to write more complicated software, and you're going to spend more time debugging it before you get it working. So it's a flexible piece of architecture that is completely dedicated to training neural networks.
Okay. So I was going somewhere with that, and where I was going is a GPU flop different than a Dojo flop? When
Not anymore.
No. What I meant by that is when they measure and they say it's an exaflop computer, is a flop for Dojo more valuable for neural net training than a GPU flop for neural net training? Or do they line up evenly?
It's not more. They would. So the thing to compare is like, what's the numerical accuracy of a flop? Once upon a time, a flop was a flop, and because there was only one floating point numerical format, everybody knew what it was. But with this proliferation of numerical formats, it gets a little bit harder to compare. Like CFP8 flops is not the same as 32-bit floating point operations. So, in the LinPack benchmark for hyperscale computing is always double precision flops. And then so that was the benchmark for a long time. And then recently, because signal processing has become a big deal, 32-bit floating point operations, that kind of became the if you don't specify, that's what you're talking about number. But recently that has all changed because neural network training, especially on GPUs, has dominated this conversation about flops recently. And NVIDIA silicon is kind of like the benchmark here. And NVIDIA has gradually been moving down to other numerical units also. They also support BFP16 in their silicon now. And so it's become a little vague about, are we still talking about 32-bit flops when we say flops, or are we really talking about other things? Well, Elon uses the term super broadly. Like he picks whatever numerical format he wants, and he talks about that many flops. And that's what NVIDIA has been doing the last few years. So I think it's fair game to do that. Now, there are some purists who will say, oh, it's not a 32-bit flop. It doesn't really count. But, it's not the flop we were talking about 5 years ago. And that's true. But that's in the weeds for most people. The thing that matters is how many numerical operations per second can you get? Because at the end of the day, training a neural network takes a certain number of numerical operations. And, those numerical operations, whatever format I do them in, that's my limiter. So if I can express the operation I want in a flop of the resolution that the hardware has, then it's fair game to use that number. And so that exaflop number is almost certainly CFP8, BFP16 flops, right? That's their highest speed, lowest resolution numerical operation, which is floating point. They could do integer operations, probably even faster than that. But he's not saying ops. It's floating point ops means you're doing floating point. That's what a flop is. Yeah. If you say op, it's integer by convention.
Well, let me try. My monkey brain is going to try to phrase this in a different way. Does Tesla get more for its neural network training out of a flop than other uses of neural net training computers get out of a flop? They don't get more. Okay, that covers it. Okay.
The whole point is just to get more flops. So if you tailor your flop to your application, a flop is a flop, and you're getting your mileage out of it. So if somebody else is using a 32-bit flop, arguably a 32-bit flop is more useful than the 8-bit flop is. And so if you're comparing across, numbers that way, then Tesla might not look good. But Tesla doesn't care about 32-bit flops. They don't need them.
Okay.
They're doing neural networks.
Okay. So, I got too many questions. You mentioned this at the beginning. When they talked about Dojo, they started with a node, then they went to the D1 chip, then they went to a tile, and then they went to a cabinet, and then they go to the row of cabinets, basically. So let's start with this. What's a node?
So, so a node, it's like the atomic unit of compute that's programmable in the system. So it's the smallest thing that you can write a program for and run it. Right. So modern computers that work at scale, typically they rather than build one one computer, one CPU and try to get it to run at a terahertz, which is impossible. Silicon can't go that fast. Instead, what you do is you combine a lot of CPUs that run at lower clock speeds and that maybe are smaller CPUs. So, for instance, the NVIDIA based HPC that they're using for doing training right now, they have 576 racks, nodes. In this case, a node is a rack computer. A node can be basically anything depending on the scale, just to make the terminology clear. In this case, when Ganesh was talking about the node terminology he used was an individual compute unit on a die. Now, a D1 die includes, I think it was 376 of these. So they've got 376 of these in a square grid on a D1 die. An individual node is you can write a program and it runs on that, and it runs with a set of registers, a set of multipliers and whatnot. And it's fairly independent of all the other nodes on the die. It could be arbitrarily independent. Now, of course, when you use it on big computations, you use a bunch of these things together. They coordinate themselves through these links that they have between each other on the network. So the node is like this. It's like a single core on a CPU. You could think of it that way.
Right. So is that substantially different from a GPU chip? Does a GPU chip typically have multiple nodes on it?
GPU chips today typically have large numbers of nodes. And now what you call a node on a GPU chip is a little bit more complicated because they kind of have nodes within nodes. And so sometimes they talk about the bigger unit as a node, and sometimes you talk about the smaller one. So on NVIDIA, they might talk about individual, multiplier units inside a thing, or they might talk about something which has like 16 of these SMUs that's cooperating and shares memory. So GPUs frequently do a thing where they have a bunch of compute. Well, they might have, thousands of compute units on a die, but they'll have them in little clusters where like maybe 8 of them share a memory together. So you can talk about the 8 that work together to share a piece of memory, or you can talk about the individual ones depending on the context that you want. In the case of the D1 chip, they really only, their architectural steps are there's a node, and then there's a D1, because each node is basically standalone within the fabric.
Right.
Or it's no more or less standalone than any other node. There's no unit of organization between the node and the chip. And then you go from the chip to the multi-chip module, which was that thing that we saw the picture of on AI Day. The thing, the tile that Ganesh showed. Then you go to I guess they put 6 of those on a level inside a cabinet.
I think they're 2 levels.
A cabinet contains 2 of these.
I think they're 2 levels. I think they're 2 high and 3 deep or something like that, or 3 wide.
It's 2 by 3 in a single shelf, and then I think they put 2 of those shelves.
Maybe that was it. Yeah, okay.
So you end up with 12 of them in a cabinet, if I remember right.
And then 10 cabinets, you get 120 of them. You get your exaflop. That's that.
Let's see. Well, the fabric that he had in his diagram was a 15 by 100 set of tiles. So it was. Is this right? Oh no, it's a 15 by 100 die, and then each multi-chip module is 5 by 5. So you've got 3 multi-chip modules by 3 by 20, and if you break that into 2 by 3 blocks, you get what, 20 divided by 2, you get 10 of those. Yeah. So
Okay.
I think it's 5 cabinets, 10 shelves.
Right.
And each shelf is 6 MCMs.
Okay, so this modularity that they talked about, you've got a node, and like at this very small level, like 1/380th of a chip roughly, you've got a node that can actually do work. And then you've got 380 of those on a chip. So the chip is like 380 or 376 or 386 nodes. And then you've got 5 chips on a tile. So you've got some ridiculous amount of compute, like I think it was 9 petaflops on
25. Yeah.
25 chips on a tile. You got 9 and then the tile, then you've got a cabinet of tiles. And really, I think the cabinet is just sort of a structure to house the idea that you just have a whole bunch of tiles that are connected to each other.
Well, a cabinet is a rack in a data center. So it's a unit of compute, which is the size of a refrigerator, right? So data center architectures work in cabinets because they know how big a room they need and how much cabling and power and stuff, right?
But the cabinet isn't really meaningful in the modularity, right? The cabinet is just an arbitrary distinction. What you've really got is we're just connecting all these tiles together in this way, and the cabinets are the structure that holds them, but they're not really part of the...
Well, the cabinet is the shipping unit.
Yeah.
Right?
It's a physical.
You put it on a pallet and ship it to the data center.
It's a physical manifestation, but it's not. The fact that you have it in a cabinet. They said we break the walls between the cabinets and connect them all together. So really, if you built like a monster cabinet, put them all in one, that would be fine.
Yeah, it's frequently cabinets in data centers. So each. You have packages within packages. You have a chip inside a multi-chip module, and that multi-chip module goes, onto a tray, and the tray goes into and at each one of these levels, you have connectors that pass data onto the others. So as you work your way to these higher and higher levels, typically your communication interface changes. And so in data centers, typically you have cables that run between cabinets. Now, inside a cabinet, everything can be chips on circuit boards plugged into backplanes. And that gets you a certain cost per gigabit per second of interconnect and a certain sort of flexibility in how you build it. But as soon as you have 2 cabinets, now you got to run a wire, a cable, an optical fiber, something between the 2 of them. And so now to go outside the cabinet, you have to have a set of these interfaces, which is designed to traverse longer distances. So like if you're going a micron, use a particular, there are things you can use. And on the individual D1 die, they have lots of little data interconnects, which are like on the scale of 1 micron in length. You're sending a signal 1 micron. Then you use a different thing when you want to go a millimeter. Then you use a different thing when you want to go a centimeter. Then you use a different thing when you want to go a foot, right? And when you leave the cabinet, now all of a sudden you've got to go 3 feet. So that's yet another thing. And that's typically the worst, most painful, slowest link in the chain of building your hyperscale computer. So people who build these things, they really care about the cabinet boundaries because frequently those are the bottleneck which most constrain your application. So I think, Ganesh would love, and maybe Tesla will do this. A really cool thing would be to just, build a cabinet that's the size of a cargo container. Build that in your factory and then ship that where you're going to go, right?
Maybe you build
and skip this slow interface between the cabinets.
I don't think we're thinking big enough. Maybe you build a cabinet that's the size of Giga Texas.
Like if they got an exaflop in 10 racks, they're thinking plenty big.
Okay.
So exaflop computers in the real world today are 50 times that size or something.
Well, 10 refrigerators doesn't sound that big to me.
No, it's not. I mean, as data center scaling goes, it's really tiny. And so they're doing this because they want to keep the coupling tight and keep the bandwidth high and keep the latency low between these various compute units. Because if you can get the bandwidth up, get the latency down, that gives you more flexibility in how you write your software, which means for a given level of effort, you get more performance out of your data center.
Okay. So something you said earlier struck me related to a question I was going to ask. You used the term first silicon. So we saw the D1 chip, we saw the tile. In Tesla vehicle terms, I think of prototype, pre-production, and production cars. So are they ready to produce D1 chips in volume? Are they already producing D1 chips in volume? Are they ready to produce tiles in volume? Where are they in that path?
So first silicon, that term is, so designing silicon is expensive. Sorry, let me put it this way. Fabricating silicon is expensive. So compared to a lot of other things, you tend to do a lot of design before you build your first piece of silicon. And it's generally the case that that chip designers, they try really hard to make their first silicon usable, functional. But you still have to build one and test it to know that it's good. You don't like do the design totally untried and then go make 1 million of them and build your data center, right? You build a small number, and for that, typically what you do is you use you buy a piece of a multi-project wafer from the company that's doing the fab. So TSMC, when you design something new, building a single wafer is pretty expensive. Designing the mask for a wafer at 7 nanometers, just the mask set is millions of dollars. And so, imagine you're building a chip and you don't know if it's going to work or whatnot. Do you really want to spend $20 million on a mask set, to build a wafer that's dedicated to your thing? Well, people don't want to do that. So what you do is you share a wafer with like 25 other companies that also want to do this. So you split the cost of the mask set. And what you do is you get a piece of that wafer. So then TSMC goes out and they make a stack of wafers. They dice them up, and each different company gets their bit and piece. So you wouldn't do this for mass production, but it's a much less expensive way to get your test chip built. So frequently that's what first silicon is. It's a piece of a multi-chip wafer, and you're able, to it reduces the overhead costs of manufacturing, but it makes the individual die much more expensive. So I think that's probably about where they are. They got a bunch of die. They're expensive die, much more expensive than mass-produced die will, but they have exactly the function that a mass-produced die will have. And so they can evaluate the design, determine if it's good enough. And if it is, they can proceed, they can drop their $20 million and build a full mask set and build it. Actually, it's possible that they can build enough D1 die with multi-chip, with multi-project wafers to do this project, right? Because they're not going to need 1 million of them.
Right, that's what I was going to say. One theory is they're not going to need 1 million of them. The other theory is, holy shit, what if they do build 1 million of them?
Yeah. It's like they'll need to build some really big power plants to keep them going, because those multi-chip modules are like 15 kilowatts a piece, right?
Yeah. So that was it. So we have first silicon for the D1 chip. I think you've explained that. Now you got the tile. And so they made their own tile. That's probably a prototype tile. They're not ready to produce those.
Everything is a prototype at this point.
No, but I mean, the chip is something like you described. It's made out of, they do this wafer and they make a whole bunch of different chips for different customers on one wafer. Okay, I think I got that. The tile is like, they can't go to TSMC and listen, we know you're making like a big thing with like 20 tiles. Make one of the tiles for us. They're building those themselves. That's probably a prototype tile, and then they're figuring out, okay, what else do we need to do? But they actually ran it.
Okay, so the only thing they get from TSMC is the die. Yeah. The tile is a packaging technology, and they're also putting other electronics in there for power.
The power and cooling. So, power and cooling.
Yeah, I mean, yeah, the cooling is external to the tile, right? The tile itself has got the silicon, connected to these heat plates, and then you add a liquid. You add a heat exchanger, a liquid heat exchanger on one side or both sides of that, so that you can extract the heat, and that's separate. That's not part of the tile. The tile is the multi-chip module with the heat sinks, and in Tesla's case, they've integrated the power electronics into the MCM also.
Okay, so the tile is something, I think they're making that in-house.
Yeah,
and
it'll be full custom.
And they've made one, as far as we know. Maybe they've made more than one, and they tested it on minimum GPT or GPT min or something. Did you see the graphic where they said, Andre, we ran your software on this? What was that?
GPT min, yeah.
What? What did they do?
OpenAI developed a set of language models that are called GPT, and there was GPT-2 and then 3, and GPT-3 is the one that said it's a 175 billion parameter model. So the GPT-3 and 2 are astoundingly capable language models, And if you want to train a big neural network, they're kind of a benchmark, right? So they didn't release well, I guess they did release GPT-2, but in any case, other people have built variations on this GPT architecture. And one of them is called GPT-10 Min, which is like, it's a minimalist GPT, but it's still a huge neural network. It's easy to write. The code for it is pretty simple, and training it is really simple because you just need a large corpus of text. So apparently what Ganesh did is Andre they built this thing, and Andre was like, we need some code to test, a decent sized neural network that will actually challenge it. And Andre's like, oh, run GPT Min on it, because you can just get this, you can download a corpus of training data off the internet, and Andre could probably write that program in 1 page of Python code, right? I mean, he's amazing. But so he can knock out a test program, and they ran it. And Ganesh is like, wow, look, it works. It works.
Sounded like,
because the thing is,
it sounded like they did it without telling him that they actually ran it. They did it without telling him, so they could say to him, hey, Andre, we ran GPT Min on it.
Yeah. I would imagine, if you asked me, if I was Andre inside there, I'm like, if you can run GPT Min, we'll look at using your stuff, right? Like it's if you can't run that, it's not debugged well enough to be worth us spending any time on it. Because Ganesh's hardware group, they've got to debug the hardware. They've got to get these device drivers written. There's a ton of stuff that they've got to do, and it's not really useful until you get it to a certain level of functionality. Andre's not going to want to waste the time of his team working on buggy hardware, right? So get it debugged to where you can run this. And so, like, if you can run GPT Min, it's working because there's a deterministic way that you can test the end result. It's really complicated to get to actually test the thing, to train it and get it up, but how it should behave once you get it built. So it's a large scale demonstration test, and you need a large scale demonstration test because this thing's got so much horsepower, right? It's got to be a pretty big model, or it's not going to sufficiently exercise the hardware for you to really know whether it's working or not.
Okay. So there was a graph that they showed that it was running GPT Min. What was the graph showing? You remember? It was sort of like a declining curve. It was like
I'd have to go look at it.
All right. I don't want to bug you at that
point. So I haven't had a chance to go through, I'm in the process of going back through this and building notes and reading back.
Okay, well, let's skip that then.
I haven't got to the dojo part
Let's skip that then. So, all right. So, well, do you have a sense of what engineering challenges remain to complete dojo?
Oh, I can tell you what it probably was, though. It's probably loss as a function of time.
Okay.
Which is it's the better the neural network get. I gave you that example of cats and dogs. Yeah. Where as your neural network trains, it gets more and more of the test examples right. And so what you do is you plot that percentage of how many it got right or how many it got wrong on a curve.
Yep.
Loss is error. So typically you start with a high loss, and as your network trains, the loss at some point it falls off a cliff, and then it gradually trends closer and closer to zero as it gets better and better.
Yeah. That's what it looked like exactly. Okay, so what do you think is left in terms of engineering to get Dojo ready to run? What do they have left to do?
A huge amount of work. But the thing is, a lot of the other stuff that they still need to do can be done in parallel. Like once you go through this process of deciding on your architecture. You run a bunch of simulations on your proposed architecture to see if it's going to be a good fit to your problem space. Then once you've settled on that, then the silicon guys, start fiddling around with stuff. At some point, there's a long process between when you first start examining the space of possibilities, which, because this is a from scratch design, we know they started. They didn't let's go buy some ARM cores and see how many we can pack on a die, right? This is from scratch. So they had a long road to get to this point. But probably a year ago, they were at a point where they could say, okay, this is what the cabinet looks like. This is what the PCB needs to look like. This is what the MCM needs to be like. So you can spin up all these independent efforts of guys that are designing all those things in parallel. And so it could be, there's a lot of work besides building that. You keep calling it a tile. I guess they called it a tile. I keep calling it an MCM. So those are interchangeable. But once they've got the tile running, it's possible that the cabinet guys have already worked out most of the cabinet stuff. And the guys that are doing the trays, they've worked out the stuff for how the trays got to work. And so maybe you just drop these things together and it goes together pretty quickly. But they're outside of that tile. There's an enormous amount of stuff that has to be done. developing the silicon, getting it into the tile, and getting the tile working is maybe 10% of the overall effort, maybe 20%, something like that, in terms of total manpower. But in terms of calendar time, let's say, I don't want to.
Okay.
You can only get such a big team on. You don't put 100 guys on the cabinet. You might put 100 guys on the silicon because there are ways to decompose that problem. But it being Tesla, they probably have 3 really good guys doing the silicon.
Yeah. So one of the concepts that they talked about when they were going through, here's what's on the chip, here's what's on here's what's between the nodes on the chip, here's what's between the chips on the tile, and here's what's between the tiles, and it has to do with bandwidth. So there's bandwidth between the nodes and from nodes to the chip, or bandwidth off the chip, on and off the chip to the rest of the tile, bandwidth from the tile to tile. How important is bandwidth, and is that part of what makes the flops hot? In other words, if you had the compute but you didn't have the bandwidth, it wouldn't be very useful, right?
No.
Can you try to explain to our monkey brains how that bandwidth matters at the node level, chip level, tile level?
So when you're building computers, there's a few kind of core things that you can talk about performance-wise. One of them is like, how fast can you do your atomic arithmetic operation, in this case a flop. Another one might be, how much memory do you have on the die? Remember, that was Ganesh mentioned they've got 1.25 megabytes on each one of these
on the nodes.
Nodes that they have. Yeah, so that's another fundamental metric. Like, how much local storage do you have? What's your bandwidth to local storage? What's your bandwidth to the adjacent node? What's your bandwidth up to scale and whatnot? But so kind of bandwidth, memory capacity, and compute, you could think of those as like 3 kind of fundamental metrics. If any one of them is inadequate to your job, the architecture is going to be terrible because you're going to have to do all this stuff to work around it. So you want each one of them to be adequate, but not. If you put a ton of effort into like making the compute run really fast and the I/O can't keep it up with it, well, your design isn't going to be optimized, right? And you can do the opposite too. You can make your I/O really fast, and so this is why you spend a bunch of time simulating your system when you first come up with your architecture. Like, for this amount of compute, how much I/O do we need at this scale? How much do we need at this other scale? How much memory do we need for this kind of problem or for some other kind of problem? Now, all the things being equal, more is better, right? Like 5 gigabytes per second is better than 1, and 50 is better than that. So these are all very crude, rule of thumb numbers. Ideally, if your architecture is really well suited to your problem, you can use all your bandwidth while you use all your compute, while you use all your memory. Then you're a good fit, right? And having more is better, but it's always a trade-off. It's almost always the case that if you try to go bigger on one of them, it costs you on the others because there are trade-offs in the reality of how you get this stuff done. So but the bandwidth is a useful thing to be able to talk about because it tells you how tightly you can couple the processes that run on these nodes. So if you start with a job that's got some scale and you want to run it on your big computer, because it has to run on a lot of nodes, you have to break it down into node-sized chunks and run them on separate nodes. When you do that breakdown, you're frequently doing something where, like, say you're taking a big matrix and you're breaking it up into 25 pieces. So you're going to run it on 25 separate nodes. Well, it's almost always the case, and this varies depending on the operation that you're doing, that there's a certain amount of communication that has to occur between those nodes in order for them to coordinate what they're working on. Like when you're doing matrix multiply, matrices are in rows and they're in columns. So there's information that has to pass between these nodes in order to do that. You can spend all your time waiting on the information from the node next to you before you can proceed with your arithmetic operations. So the node can end up being massively underutilized if it's waiting on communication or if it's waiting on memory, getting starved. In fact, we know that they don't have all the bandwidth they could possibly want because they decided to make the nodes multi-threaded. They can run 4 threads on a node. And the reason you do that on a superscalar processor is because you anticipate running jobs that can't make optimal use of the register or memory bandwidth or IO bandwidth. So you run 4 different jobs simultaneously. So when one of them is stalled, waiting for access to a register, access to some memory, another one can proceed. So you might have, if you've got 25 nodes, you actually generate 100 threads. So you're running 4 threads on each one of these nodes, and they're all kind of working together to exercise to the greatest possible extent the hardware to its fullest.
Okay. All right. One of the questions I had was, Elon specifically was asked this question on Twitter. Does he anticipate Dojo neural net training as a service? And Elon said yes. So can you talk a little bit about the market for neural net training as a service? Where do you see that now, and where do you see that going in the future?
Yeah, I mean, it's going to be a big market.
Can I just...
It's not a... Yeah, it's a tough market to talk about. Like my general sense of things is that offering Dojo as a service to the outside is a huge side task for Tesla. Like building a piece of hardware to use inside is much easier than exposing it to the outside world. Like people frequently say, like, Tesla could just sell their FSD silicon, and that misunderstands the nature of building silicon for in-house consumption versus selling it to the public. Yeah. When you build silicon and you use it inside your own company, you don't have to. If you sell a piece of silicon externally, or you sell a system or a service externally, you have to have an interface to that service, and you have to document it. And because customers are going to go off and they're going to do a ton of their own work with a certain understanding of the service that you're going to provide. And for these technical services like silicon and whatnot, those are very complicated uses, and they have to be specified in great detail. And with silicon, if you make something that you're going to sell to a consumer, you have to characterize the device sufficiently that you know that you're actually giving them what you say you're giving them. And it turns out that designing a piece of silicon so that it meets those characteristics is a large additional burden on the people designing and getting the chip to work, which you don't have to do if you just use it internally. If you use the silicon, because the guy who designed the chip, he just goes to the cubicle down the hall and he talks to the guy who's going to use the chip. And if that guy finds a problem, he can just come down and say, hey, this thing didn't work. And the guy can sit down, run the simulations. You're like, oh, you're right. We said that would be 1.2 nanoseconds. It's actually 1.3. That's because the temperature's too high. But you could do this instead, and that would work. And you can't do that when you have 100 outside customers that want to talk to the guy. Right. So for Tesla to sell the silicon, the FSD chip outside, requires them to add a lot of manpower and do a lot of work that they don't have to do if they just use it in-house. And similarly for Dojo, right? If they just use Dojo in-house, the amount of work that they have to do is a lot lower than if they offer that service outside. So my read is, as long as Tesla is manpower constrained and super focused on their core mission, that they're going to, unless they really think that this will enable them to make money that will help them forward their mission, and that they have the surplus manpower to do it, they won't do that.
Well,
and now eventually, sure, they could do it. Like if we're talking 10 years down the road, sure, why not? But I would not expect to see Dojo as a service for other people in like the next 5 years kind of time frame, because it's just too much work to expose it to the outside world.
Let me go with this theory. Theory is that at some point they're going to have FSD mostly solved, that the cars will drive themselves. And then, I think I know the answer to this question already, but what do you do with Dojo once you've solved the main problem? Well, now we know the answer is you make the robots work. So you still use it in-house for that. But, once you've built one Dojo, why wouldn't you build another one and run that one as a service? Or then that leads me to my next question, which was,
it's 2 years from now they'll be able to build a better Dojo.
Well, that's what they said. They're already working on generation 2. The guys who designed the Dojo 1 chip, I guess, are done, right? We're satisfied D1 chip is good. We don't need to re-engineer D1 chip. So now let's get those guys working on the D2 chip or the generation 2 chip. And they were saying that they anticipate a 10x improvement on the next generation Dojo, which would mean 10 exaflops. So my sort of thought was, well, does it make sense once you've got Dojo working to build 10 dojos, or does it make sense to go ahead and build generation 2 Dojo?
Yeah, well, so that's always a trade-off, right? Yeah. Anything you can't make really good use of in the short run, you don't. It's like buying a laptop these days. 2 years from now, there's going to be a much better laptop. It's going to be cheaper, right? So how much do you spend on your laptop right now? Well, no more than you can extract from it over 2 years, right? And that's a problem with dojos too.
Let me ask you this. My laptop, I have a MacBook Pro. It's about 3 years old, and it has become overwhelmed when I try to do video editing and live streaming. And somebody told me, oh, you got to get the new M1 Macbook. Even the MacBook Air is like way better. I have a MacBook Pro. I have like a nice MacBook Pro. And they're like, no. You need the M1. The M1 MacBook Air is like way better at video editing and video whatever than even a 3-year-old MacBook Pro.
Yeah.
So, okay.
I actually do a bunch of video transcoding. So I've got this, I have, the previous state-of-the-art Mac laptop, the 16-inch totally loaded MacBook Pro. And then I bought this, just for jollies, I bought this 13-inch M1 MacBook Pro. This thing crushes. It costs like a third as much. Yeah. And when I say it crushes it, it's more than an order of magnitude faster. Like this thing can transcode video all day long, and it doesn't speed up the fan. Like on this big machine, I can't do video transcoding on the battery because it'll drain the battery dead in like 30 minutes if I try to transcode video with it, right? This will transcode video for 10 hours. It's nuts. It's like night and day. It's shocking. And this is a different silicon makes, right? Yeah. Because Apple's the silicon that Apple is putting in this thing is tailored to exactly what they want the laptop doing. Right. Which, the silicon that they bought from Intel for the other things, like it's a fine laptop. It's, it was the state-of-the-art chip for doing that kind of stuff at the time that they got it. But, this is the advantage Tesla gets over designing their own silicon versus buying it from NVIDIA. They've got the silicon that does exactly what they want. And at the same cost and the same power and all the other stuff, they get 10 times the utility, just like Apple is getting right now out of their M1 silicon.
Yeah, I was just really quick. People are telling me to stop the laptop talk, but I was doing live streaming with my laptop plugged in. And I had a camera plugged in, a microphone plugged in, Ethernet plugged in, and the power plugged in. And the battery ran out. The battery died in the middle of a live stream. I started at 100%, and it had power plugged in, and I was using it so much. And I had ice packs under it to keep it cool. Anyway, so that led me to what I'm using now. I use a PC. So let's move on from that. So how many Generation 1 dojos do you think they'll build?
One.
Think they'll just build the one and they'll go on to the next one? Next generation?
I think, the second gen, third gen, they'll come together faster than the first gen will. They're still building the team. They're still learning how to get this stuff going. Dojo's a novel architecture. It's very likely the second gen will build on the first gen architecture. So everything will go better on the second generation than it did for the first generation. I don't know. In a sense, designing the first generation neural network accelerators, in a sense, they're kind of easy because there's all this low-hanging fruit that you can go after when you do a custom design as opposed to something else. You don't have to make it perfect. You can just pick the 4 or 5 things that like CPUs and GPUs are bad at and make those better. And you get something that's dramatically better. And it might still be easy to design and you might get it to come together really quickly. When Google did their first TPU, it was a shockingly simple piece of silicon, but it was just crushing the GPUs that they were using at the time for doing inference. In fact, Google had this problem where they wanted to go big on neural networks in their data centers, and they realized they don't have enough data centers because these things are so compute intensive that if they really started pushing out these neural networks that they were using in their search capability and their language translation and whatnot, they literally could not build data centers fast enough to do it. And that was one of the things that pushed them to develop their own silicon to do this. And all of a sudden, they were getting nodes that were 100 times as capable in terms of the workload that they wanted to do. So all of a sudden, you need 100 times less data centers. which when you think about how many data centers Google builds, that's a lot of infrastructure, right? It's worth solving the core problem and proceeding efficiently from that point. So, that's very likely to be a similar path to what Tesla ends up getting, unless they're extraordinarily fortunate in terms of having very few problems and a very straightforward runway to getting everything working. I would not expect them to build, but I mean, one dojo is a hell of a lot of dojo. And the other thing is it'll take time to learn to make best use of it, even after it's debugged and fully working. There's all of this software infrastructure that you've got to develop in order to make good use of it. You have to learn to port jobs to it and discover the trade-offs in that. And in the meantime, that's why even though they've got Dojo, they're building these really big Supermicro based, NVIDIA, A100 based hyperscale compute clusters that they're doing. And I wouldn't be surprised if they build another giant NVIDIA cluster, even though they've got Dojo in the works, because there are going to be workloads that hardware continues to be really good for. And as their mission expands and their ambition expands, they'll have plenty of stuff to keep all this hardware busy.
But wasn't that the pitch, that if we know the Dojo is good if they tell us they want to turn off the GPU cluster?
Yeah, it's GPU clusters. They've got some. Once again, Tesla is designing Dojo for doing neural network training, and it's going to be really good at that. But if you want to train from video, you have all this video processing that you want to do, and Dojo might not actually be as well suited to doing the video part of that. So maybe you run that stuff on your, there's all kinds of stuff that GPU will continue to be useful for, especially because one of the reasons that NVIDIA is so dominant in this space is because the libraries and the tools that they have for letting people make good use of their hardware with minimal engineering effort is really like nobody else is even close. They're just like crushing it on that scale. And Tesla can take advantage of that.
Okay. I just want,
as long as they're buying the NVIDIA hardware.
I want to come back to this idea of Dojo as a service or neural net training as a service, because Kathy Wood's ARK Invest is, I don't know if you read their Big Ideas white paper. They did a Big Ideas white paper, and they're projecting that there's going to be this huge market for neural net training as a service in the next 5 to 10 years. Do you see that the market is there, and it's just a question of whether Tesla wants to play in that market?
Yeah, it's the question. Will come down to does Tesla internally have a better use for it then? It's do we invest our profit in our business, or do we return it to shareholders? Right. As long as they can invest their Dojo energy in their own business and get a good return on it, return on mission, right? Right. As long as they're getting good return on mission, then the attraction of going outside. Because the thing you make by opening up to the outside world, is mainly money, right? It's another business, another source of revenue, and you can use the money from that to build other kinds of stuff. But, if you're making plenty of money in your other stuff, then maybe that's not the attraction. It's a complicated trade-off. This stuff isn't free. You have to take your smart people and you have to take them off of building Tesla bot or building starships to go to Mars, and you have to put them on this training thing, and you have to ask the question, is that the best use of my people?
Yeah, good point. No, and actually, I was kind of wondering. I'm heading towards Tesla bot, not quite yet, but is the FSD chip in the car the right chip to go on the bot? Is the Dojo that's optimized for training the car the right Dojo that's to be optimized for training the bot? Or is the idea that maybe Dojo Generation 2 and maybe the inference hardware version 4 or version 5 are really optimized for bot because the space that it operates on is different than the space that a car operates on? Or is that irrelevant, that the training is the training and the neural net's the neural net, and it doesn't really matter?
The neural net for the bot will be different.
Okay.
I use this metaphor, and I think it's apt. Analogy, not metaphor. I use this analogy, which is that FSD is like going to the moon, and the humanoid robot is like going to Mars. It's they have a lot of things in common, but the humanoid robot is quite dramatically more difficult than doing the car is. In the time between, FSD is mature and widespread, it's never going to be done. Right. Just like laptops aren't done, computers aren't done. It's never going to be done. But it'll in the time between FSD becoming widespread and the bot becoming widespread, all of the technologies that underlie this stuff are going to move a long way, because the bot's not going to happen in 2 years. Right. I mean, we'll see prototypes, maybe, that kind of stuff, but it's not going to go into broad use in a short window of time. And so, yeah, the silicon that goes in the bot is going to be really different than the FSD computer today, because it's going to be 5 generations removed from the silicon that's going into FSD now. It'll be, 1 nanometer. It'll be quite dramatically more capable, quite dramatically more power efficient, and they'll know a lot more about running these neural. It's the understanding of the best way to go about building a network is very rapidly advancing, and it's just since Tesla started working on FSD, and the FSD team is constantly trying to incorporate these latest findings from people outside the company into what they're doing, and that'll happen with the bot too. So,
okay, one quick thing: Elon said hardware 4 in a year or so with Cybertruck. Did it sound to you like Cybertruck was delayed until maybe Q3 2022? Did you catch that bit?
I did hear him say that, and I saw people interpret it that way. I thought he was talking about the time frame for hardware 4. That I actually tweeted right after his comment on that, like, hey, hardware 4, we'll get it inside a year, or whatever the deal was. Other people took it as a comment on Cybertruck availability, and I didn't hear it that way, but maybe I just wasn't thinking in those terms.
I mean, the way I heard it was Cybertruck will ship with the upgraded cameras, hardware 4, which is going to be 4 times better. What does that mean? So hardware 4 or FSD computer version 2 is going to be 4 times better. What does 4 times better mean? Does it mean 4 times the size of the neural net, or? Yeah.
I mean, that's how there are lots of different ways you can measure it. And, whether you talk about the amount of memory on board, or the IO bandwidth, or the number of flops it can do. I mean, these aren't all going to be exactly the same number, but the simplest metric is just like, how big a neural network can you run, or how much neural network can you run, rather than how big, because they run a lot of neural networks right now. They don't run one big neural network.
Is the training that was done on the current hardware, like you got this new hardware 4 chip, you got these new cameras, you got this new vehicle. Is the training that was done on the hardware 3 chip transferable to the hardware 4 chip, or do you have to start over from scratch training the new computer?
Well, it depends. Okay, they won't have to start over training. Neural networks are an abstraction, which can be mapped onto various pieces of hardware, which is why, for a long time they were running the AP2 networks ran on hardware 3 and they ran on hardware 2 simultaneously. The neural network was the same. And then after the neural network is trained up in the data center and they quantize it, you go through 2 different backend processes to make the binary that you run on hardware 3 and a different one so they'll have something like that for hardware 4. Over time, just as I think we've seen them move from neural networks where the architecture was optimized for running on the GPU that they had before the FSD chip came out, toward leaning more towards what runs well on hardware 3. So there will be a trade-off. Like, upstream, you can make decisions that favor one platform or the other slightly, but they are approximately fungible. I mean, to a first approximation, you can say this one has capacity 2 and this one has capacity 10. And I can run the same thing on the 2 with that difference in scale of capacity. And, so hardware 4 will be 4x the capacity of hardware 3, according to, Elon's comment.
Okay. So I've got this question for you. I want to dive into Tesla Bot. I got one last thing I want to talk to you about before we go into Tesla Bot. Do you have time to cover a little bit more?
Yeah, sure.
Okay. So I don't know if we've talked about this before, but I have this idea, or I should say more than idea. I started working on this. I'm paying engineers to design. I've decided I'm going to build a small EV company. It's a small company that builds small EVs. I'm not kidding. I'm serious about this.
Are these radio controlled RCs
well, in the short term, it'll be radio controlled. It is the design is then building something that will be designed for self-driving from the beginning. So you're building it with no steering wheel. You're building it with no pedals. You're building it with, you're trying to eliminate the best part is no part. I'm trying to eliminate as many parts as possible. So I'm getting ready to design and then build an alpha prototype and then go from there. And the plan is to self-fund it as long as I can. And if the more Tesla stock goes up, the longer I can self-fund it. But eventually maybe crowdfund and get a loan. And then I actually have this other crazy idea about doing a housing startup. And I'll say it this way. Elon talked about urgency. If you saw the Everyday Astronaut interview, that we have to innovate with extreme urgency, because if you don't innovate with extreme urgency, then you tend to regress. Right? And I see that now. I see that in everything he's doing. And I felt like when I was watching that, it was like, look, I'm 50. He's like saying, I'm 50 years old. I got maybe 25 years left before I'm useless. And I actually, before I saw that interview, I kind of had this attitude in my own head. I'm 55. I might be useless in 20 years. What am I doing for the next 20 years? And I want to do something more than sit on the couch and watch Netflix and Amazon Prime. Right? And I love talking to you, and I love making videos, and I'm going to keep making videos, but can I do something more? What can I do with some level of urgency to like make a difference somehow? So first of all, does it sound crazy that I'm diving in? Look, it's my money. I can throw it in there. Does it sound crazy to try to pursue this? I mean, I suppose everything, people told Elon he was crazy to build a car company, build a rocket company, right? Does it sound so crazy I shouldn't do it? Or do you have any thoughts on that?
Startups are crazy. To do a startup with the expectation that you're going to succeed is crazy.
Oh, I expect to fail. I expect to fail.
Yeah, it's like of the startups I did, I had one great success and I had a whole lot of like really painful failures. Yeah. And that's just part of the thing. When I was in college, my calculation was that, startups, you got a 10% chance of success. So I budgeted for 10 startups, and that was how I proceeded forward with the thing. So yeah, it's crazy. Any individual startup is going to be crazy. If it's worth doing, it's probably crazy. So that's my
attitude is, if I didn't do it, it would be crazy because I got to do something. I mean, maybe it's not the right thing to do, but
you only got one life.
Yeah.
Right? We all got a limited amount of time, and once you've got the basics taken care of, you have to ask the question, what is worth my time? What do I want to spend the essential dilemma of human existence is how to spend the hours of your days, right? Yeah. You have to make that decision.
So let me turn that on you then, because that's the reason I was going there was, it's not really about me, it's about you. What do you see? I don't know how much time you think you have left. And maybe we're both going to get Neuralinks and it's going to prolong our usefulness, but what do you see yourself doing for the next 10, 20, 30 years that you feel like is going to be special?
A long time ago, I gave up on trying to predict what was going to happen down the road, because my experience in life is that at every point in my life, I've been doing something that 5 years ago didn't even occur to me. And I no longer try to figure it out. I just, at any given point, I take the next step. Well, and I don't look that far down the road.
But I mean, other than doing interviews like this, what are you working on now? What are you working on right now that you're excited about? Or maybe you can't talk about it. I don't know.
It'd be a long conversation.
Okay.
I have many things I'm interested in. I thought you were going to go with this because people keep asking me, why don't you go work for Tesla? Right?
People actually asked me to ask you that question, and I thought this was a better question.
Yeah. Okay. So I worked for companies. My belief, I started companies, I worked for companies, I worked in big teams, I worked in small teams. And my belief, is that if you do that, right? You prioritize succeeding there. And if you're not going to do that, go do something else. So I spent a lot of my career really focused on the needs of the team. And it's not, but the thing is, at heart, I'm a generalist. I like doing lots of different kinds of things, and I do a lot of different kinds of things. And so the reason why it would be a long conversation is because I have a lot of different things that I am doing, and I like that. And I have the luxury of being able to do it, which I didn't have for decades when I was very busy with trying to make my company succeed, my team succeed.
Yeah. No, actually, I would say most of my life, I'm an attorney by training, and I had a career as an attorney, and I always kept finding other things to do. So the reason I moved to Florida was I built a website that sort of is an offshoot of the law firm that ended up making more money than the law firm. And then I shut down the law firm and moved to Florida, and then I tried real estate, and then all of a sudden I'm a YouTuber. Like, I just keep doing stuff, and whatever works, works, and whatever doesn't work, we drop. And even in the law firm, we had like 3 or 4 different things that we did, and one year this one did well, and another year this one did well. And okay, so let's turn to Tesla Bot.
If you'd asked me a year ago if I was going to be like talking about neural networks on YouTube, I would have told you were crazy, right? And I've spent so much time doing that over the last 6 months. It's crazy. And like why am I doing this? Right? Like I don't need this. Like it's a non-trivial amount of risk to being to exposing yourself, and and I'm not making any money. I don't have an agenda. I don't have anything to push. But
you like talking about it.
I do really like talking about this. And a thing that I after I agreed to do a couple of them, a thing that I realized is that I learn a lot from these conversations, because it makes me think about this stuff that I'm thinking about in different ways, trying to explain it to people. And I get feedback. It's like, a lot of questions are relatively simple things, and they don't give a lot of insight. But occasionally I get questions that are like, oh yeah, that is a really good question. I should really think about that. And so what I'm finding is that my understanding of the thing is improving significantly as my attention sort of gets diverted to these different things. And that has a lot of value to me. It's made it more than worth the time investment of figuring out how to do this and getting it. It's like, I'm super introverted. Yeah. It probably doesn't it can't possibly come across. I am incredibly introverted, and I get so nervous doing these things. The first couple of ones I did, I was just like,
it doesn't come across at all.
In sweat by the end of the thing. So it was really painful to get over that, but it's been worth the investment.
Yeah. Somebody mentioned the pet bear in your backyard. I think it's more than one, isn't it?
So I live up against a wilderness reserve, and all the wildlife. We get mountain lions and bobcats, you name it. This morning I was standing in the front yard, and some coyotes ran through. There are 5. I've discovered recently that when I trim my bushes, I cut the branches and I lay them down and I let them sit there for a week, because the deer will eat all the leaves off, and that makes it a lot easier to just chop them up and stick them in the trash. It's just like, So we have so much wildlife, it's nuts.
Cool. All right, so let's turn to Tesla Bot. Before you came on with me, I did a whole bunch about Tesla Bot, but so I have some questions. Well, first question, how much do you think it will cost Tesla to build the Tesla Bot at scale? Once they're building them in a high volume.
Well, at what point in time, right?
Like 5 years from now.
When Tesla bots are building other Tesla bots, they'll be free, right?
Right.
It'll be, because the Tesla bots, they'll be doing the mining, they'll be doing the design, they'll be building the other Tesla bots. You've got the whole self-replicating thing done, and so the cost is negative.
I guess I would say in the short run, once not prototypes, but once they build the first machine that builds the machine, they build the first factory to build the Tesla bots, and they're spitting them out like at the stage we're at now with the Tesla Model 3, let's say, right? They've been producing them for 3 years now. They've ramped. How much do you think it would cost to build that for scale?
I did a design study 2 years ago looking at humanoid robots, asking the question, like, can you do it for $10,000? And what new technologies are needed? What new materials, and blah, blah, blah. And at the end of that design study, my conclusion was, you can do it for $10,000. You have to get to scale. What is scale? Scale is millions.
Yeah.
It's not billions. It's not thousands. It's millions. So do you sell them for $10,000? I don't know, but you can build them for $10,000. That's what I think. That's the scale. It's not 1,000. It's not 1,000,000. It's not 100,000. Right. It's $10,000.
So here's my take on it, and tell me why I'm wrong. Let's say a $50,000 Tesla weighs about 4,000 pounds and has about 10,000 parts. Now, maybe with the front and rear castings, they've gotten the part count down, but it's in the ballpark that a $50,000 car weighs about 4,000 pounds and has about 10,000 parts. Tesla Bot is supposed to weigh 125 pounds. So in terms of total material going in, you're talking about 1/30th of the mass. And then my guess would be that you're probably not talking 10,000 parts. You're probably talking about somewhere between 2,000 and 5,000 parts. So the cost in that sense should be dramatically lower than the cost of building a $50,000 car, which of course the $50,000 costs Tesla $30,000 to build, right? So to me, the cost should be $10,000 or less because of the amount of mass going in, the number of parts going in. It's just a matter of figuring out how to make the manufacturing work so that you do you put the molecules together in the most efficient manner, right? And I don't know. I think they said something like 40 actuators. There's a bunch of different parts in there. I don't know how many moving parts. I think a bot might have more moving parts than a car. I'm not sure about that. Because there's a lot of different things that are articulating in a bot, where a car, it's got four wheels turning.
It's on the same scale. It's not going to be 10x more or 10x less. And it depends on what you consider a moving part. Like, is every ball bearing in the drivetrain a separate moving part? Or do you count the ball bearing? Or do you count the drivetrain? That kind of. So it can be a little complicated. If you just consider axes of rotation, right?
Yeah.
So steering is, there's 1, 2, 3, 4, plus 4 for the doors, 8. And then the seats each have 3, 4, so you get to maybe 40 actuators, 40 axes of movement in a car, something like that. So it'd be the kind of same scale. So
does my analysis that you got a lot less mass, you've got a lot less parts overall, that it should cost a lot less to build it than a car? Does that make sense, or am I missing something?
Okay, well, now apply it to this,
yeah.
Right? Because this is $1,000, and it's way less than 1,000th of the weight of a car, right?
Right.
Yeah. So
I'm not saying
things don't scale.
I'm not saying the cost is 1/30th of the cost of a car because it's 1/30th of the mass. I'm just saying it's definitely less than half the cost of a car. If it's 1/30th of the mass and fewer parts.
That Boston Dynamics makes a robot, and it costs more than a Tesla. In fact, they make a dog robot.
But they don't make them at scale.
More than a Tesla.
But they don't make them at scale. And the phone they sell it for $1,000. That doesn't mean that it costs them $1,000 to make it. I'm talking about manufacturing cost, not sale price. And a lot of the cost of this phone is the software, not the hardware. I'm wondering the cost of building it rather than just starting with the cost of building it and then the sale price I was going to talk to you about next.
The $10,000, I think it's hard to, if you want to try to get really precise, you have to pick a moment in time, and you have to make very detailed assumptions about the design. So we're only speaking very broadly.
Yeah.
And that's why I say like $10,000 is the right broad. It's not $1,000 and it's not $100,000. $10,000 is the right order of magnitude for the scale of the thing. Now, if you want to talk about, well, could you do it at 5,000? Well, with a certain set of assumptions of scale and features, yeah, you could do it for 5,000. Will it be 20? Will it be 30? Will it be 50 when they start selling it? Well, that depends on market dynamics and what set of features you have to go into and what kind of scale you can start at and that kind of stuff. So but like, I think at this point in time, it's not necessarily useful to try to get a lot more specific, because at this point in time, it's really hard to say within say 2, 3, 5 years exactly when you will be able to build a humanoid robot with a set of features that is a good enough match to the applications that people want to apply it to, that you can sell 1 million of them. Because that's kind of like my threshold is like, when do we have 1 million? What does it look like then? And much like FSD, I think Elon really thought back in 2016 that they were going to have basic FSD working in a couple of years. I don't think he was blowing smoke when he did that. FSD is a hard problem. Everybody who's tried to design self-driving cars has, and as Elon's pointed out a bunch of times, like, if you're not over optimistic, you never start, because these problems are really hard. So, unsurprisingly, they take longer than people think they're going to. So when do we get FSD? That's still an open question. There are no existence proofs for FSD in the world. Like, I don't think what Google has driving around Chandler, Arizona really counts at this point, right? Because it's not fully independent of people. I mean, Rodney Brooks's criticism of it is he's a famous roboticist that opines on these things. And I think he has a fair criticism when he says it's not sufficiently independent to meet the bar of being a self-driving car yet. Now, they could get there in a year. They could get there in 5 years, but we don't really know until we see the answer. We don't. Okay, now multiply that by 100, because that's how hard the humanoid robot is, right? There's going to be tremendous uncertainty on when the software is done. And like if they get the software to a useful state in 2025 versus getting it to a useful state in 2030, the hardware is going to look really different, because the technology that you have available to go into these things is going to be dramatically different in 2030 than it is in 2025. And that's why I feel like it's hard to talk a lot about this kind of stuff, but you also kind of don't need to. The thing is, you can look at the world today and you can say, well, if it was $1,000, what would you use it for? If it was $10,000, what would you use it for? It was 100,000, who buys it and what do they use it for? And I think today, and I think in 2030, the answer is going to be roughly the same. Like what you would buy and use something for like 10,000 or 20,000, that kind of scale for, is different from something that's $100,000, and it's different from something that's $1,000. And I think the humanoid robots, they're going to slot into that kind of space.
Okay, so I'm gonna take the generic manual labor. It could be a roofer, it could be whatever. There's a lot of different kinds of jobs that are a lot of manual labor, a lot of what Elon's described as boring, repetitive work. For me, roofing, the most dangerous jobs are like roofing, logging, fishing, and I would say working in space. Working in space is a pretty dangerous job. But let's just starting with sort of imagine, I hate to do it, but imagine a generic job that somebody does that's got a lot of manual labor. To me, the idea that the bot replaces the laborer completely, that one worker completely, is probably wrong. That when that worker's doing their job, there's probably some parts of the job that are sufficiently boring and repetitive that you can have the bot do it. And there's some parts of the job that maybe you need a human to do in the early stages of the bot. So
pretty likely that what you see as this technology get introduced, if you're in a construction site, is that, in year one, there's one robot and 10 guys, right, doing the job. And then because there's only so much work you can give the robot its capability. As the robots get better, you add more robots and you have fewer guys, or the same number of guys, but they're building more houses maybe. But the point is, the fraction of the workforce, the fraction of the work that you can hand over to the machine, that'll be a moving target over time.
Right.
And and maybe there's a day when the robot gets in the truck and he drives the truck and he takes all the lumber and he builds the house, or he and his crew of robot homies, right?
Well, I mean,
it all done.
Honestly, you drop 20 of them in the back of a Cybertruck and you send them to the job site, right? There's 3 humans inside the cab and there's 20 bots, because the bots don't need the space.
When the Home Depot parking lot is full of bots.
Yes, exactly. You just pull up to Home Depot and the bots hop in the back of your pickup. Yeah. So the picture I had was, let's suppose the bot, just to be simplified, the bot can do half the work that worker can do. And you've got 10 workers on the roof. And thank you, Noah Jones, for your support. If you had 10 workers doing the roof, and now you can have 5 bots do the work of 5 humans. One bot, you have 5 bots, and maybe you only need 5 humans left to do the job, so you're 50-50, right? If you've replaced, and let's say the average worker costs the employer $50,000 a year. That's not just pay, but pay and benefits and other things that go along with it. If you're able to replace, let's say, one worker with a bot, and keep in mind, the bot can probably do twice as much hourly work, right? Can work twice as many hours, right? The bot doesn't need to, it needs to recharge. It doesn't need to stop for a meal. It doesn't need.
Humans are amazingly capable in our physicality.
Yeah.
So building a robot that has the dexterity and speed,
Right.
that's going to be a challenge for quite a long time. I think if you're doing the calculation in the cert run, you probably want to assume that a robot, in terms of work per unit time, is doing half or a quarter of what a human being can do.
Right.
That they're moving slowly.
That's where I'm going. They're doing half the work that a human does. So if they do half the work of a $50,000 a year job, then they just saved the employer $25,000 a year. Right? And now,
and then there's the question of how long the robot lasts. Too,
right. So if
over time.
But if the robot lasts 2 years, it's paid for itself. And if the robot goes more than 2 years, then it starts paying back. And my God, Elon's going to shoot for robots that last 10 years. I mean, maybe.
Yeah, that's, that might not be the calculation starting out, because it may be that the early applications are, that, I want a robot to stay with my mom as she gets older. And, its utilization rate might be super low, but I'd rather have a robot, with my mom than have a rotating set of, assistants that, I mean, there are issues with like
Well,
that.
that's
Especially
higher
as people
value.
get
Just to be clear, that's higher value. Because if I want a 24/7 aid with my mom, because I have, my mother's in an assisted living facility. If she was at home and she broken her collarbone and I had to have somebody with her 24/7, that's a lot more than $50,000 a year to have an aid with your. And the robot isn't going to be able to do everything that mom needs, right? So the robot's going to have to call somebody to come over and help when something happens that it can't handle. I think,
to me, this is similar to the full self-driving, economics calculation that we talk about. When I started drilling down into full self-driving, like the economics of the fleet thing, I started realizing that we basically assume that a taxi driver and a full self-driving car are basically fungible. They're providing the same service, but they don't provide the service in some significant ways. Like there's a non-trivial population of people who don't want to get in a car driven by a stranger. Right. And having a robot from some, large name brand company that you've used a bunch of times show up and drive you someplace, that's actually a feature. I mean, it's not necessarily there's a very significant space of applications where the thing is more valuable because it's driven by a robot or because it's done by a robot than it would. And that's really the place you want to deploy to first. So the basic economic calculation that you do, like what's the service worth today for what people pay for. In the beginning, that's not the way the calculation you want to do the calculation, because you initially deploy to places where the way that you're doing the job is an advantage relative to what might be the most common way of doing that. So I'm kind of expecting FSD cars to charge more than Ubers when they come out, and even so to have a big enough market that they can scale very large over time, before we get to a point where they have to come down to Uber prices and so on. And I think the robot, the Tesla bots, it's a similar kind of thing. There's a space where the fact that it's a robot is a really big advantage because it's dangerous, or because, you need somebody who can't get COVID to do this job. I mean, there are situations that robots just win. Well, or, you want a security guard, one that never sleeps is nice, and where you don't have to change them out.
So let's go forward 10 years, let's say. You've got better hardware, they got the cost of manufacturing down, and you've got better software, and they start to become very capable. Maybe 10 years, maybe 20 years. I think Elon kind of said this, but would you say that the total addressable market might be infinite?
Yeah, let
me say that it's so large that you can't make enough ROP. Sorry, go ahead.
The upper bound is absurd. Yeah. It's fun. It's like Karpathy's comment about in the limit. You can remember the world. Well, in the limit, there's no limit to how many robots you want. It's like after Mars, maybe we terraform Venus. That'll take a lot of robots too. Or I look in the sky and I see the moon, and what I see is building material. Right?
Oh my goodness.
Like you can, you want to build livable real estate, disassemble the moon, put it in orbit around the Earth, around the sun, around the other stuff. Like that's a lot of labor, right? We can keep robots busy for a long time disassembling the moon and building human habitats, right? Because the solar system, you could put a quadrillion people in this solar system, right? Before we even have to go looking for other things. If all you need is a comfy place to put your recliner so that you can sit in front of your TV and watch Netflix, we can build a lot of that with the raw material that we have within like half an AU of the Earth.
Yeah. Okay. So I think we probably should,
without damaging the Earth's ecosystem.
I'm just going to say maybe we shouldn't disassemble the whole moon. Maybe we need like 90% of it to stay in orbit for whatever.
When there's 50 trillion people and they want to, we might have a different calculus.
So first of all, thank you to David Life for the support. He said, given the possible time to FSD and Mars, the robots will take 20 years minimally. Okay.
Sure, that's possible. It's really, really hard problem.
I really picture,
but it's also a moving target. As we do with FSD, we say, a lot of the dialogue about FSD sort of assumes that there's this stopping point, and there's not a stopping point. There's a day when it can do certain jobs, and then the jobs it can do at a particular price point, just, that boundary just keeps moving over time. And then, when they're 3 times as safe as people, you have one value proposition. And when they're 100 times as safe as people, you have a different value proposition, because people can't drive cars at that point because we don't let them anymore.
Right.
Right. And the robot thing is going to be like that too. It's going to be a moving target, and it's hard to talk about. It's hard to talk in a lot of detail about the application space without making a ton of assumptions that are unlikely to be right.
Right. But when I think about use cases, I mean, obviously there's, like, I think anything dangerous. So working on roofs, logging, there's certain jobs we know are dangerous, and certain jobs, like honestly caring for the elderly, it is very costly to care for the elderly. And if you can have bots that can take care of a lot of things for them, that's reasonable. But the one that really stands out to me is the most dangerous job is space. Right? So if you can have bots assemble your space station, if you can have bots do asteroid mining or lunar mining, if you have your Martian colony and something needs to be done on the Martian surface, you can send a guy out in a spacesuit, or you can send a bot out. If the bot can do the same job, why would you send a human out there to risk his life? And especially when you can, my calculation, you can send about 2,000 Tesla bots to Mars in one ship. You might be able to send 100 humans or 50 humans, but you could send, it's 50 kilograms, ballpark 50 or 55 kilograms for a bot. And they have 1,000-ton payload, or 100-ton payload. So it works out to about 2,000 bots. And they don't need to breathe.
They don't need food, water, change of clothes.
They don't need life support.
There's all kinds of stuff they don't,
You probably need to keep them above a certain temperature to stay, warm. You probably don't want them at absolute zero. But
build them with heaters.
Yeah, but the cost of doing that, it's great. Jarno Tiny says, "Greetings to James Douma. You're awesome." And thank you for your support, Jarno. Okay, so take a step away from the use cases for a second. I envision you have sort of like, because the way you described it the last time we talked, a general purpose humanoid robot. Mm-hmm. If you go to the Matrix and they load Kung Fu into Keanu Reeves, right? Mm-hmm. Is it where the general purpose robot can do everything that the dojo for the bots trains them to do everything possible? Or is it like, let's train this bot to do this function? Like I bought my general purpose bot. I want this bot to do this task. Let's download the Kung Fu module. And I want this bot to do the roofing module, and you'd have different modules that would be downloaded to the bot to do different tasks. Or would it be every bot learns to do every task?
Well, it's funny because the hard part is the foundation. And then the stuff that you do on top of that. Like, if you have a robot that can cook, having it fold your laundry, that's just a licensing. There's no actual real capability increase necessary to do that, because you've got, at a minimum, you have to get to the level of sort of dexterity, physical coordination that a human has. And once you get to that, then all the jobs basically open, and you don't really need any significant amount of additional sort of development effort. Like all of the stuff that you can do, you tell the robot, like, I need to fix my chair, look it up on YouTube how to do it and fix the chair, right? I mean, because that's general, is you instruct them via language, and then they can self-expand by looking at examples of people doing something, right? So now, is that how you sell the robot? Is Apple going to charge you, separately for some functions and for others? I mean, it wouldn't be surprising if that's, we do that with every other thing. Right.
Well, I mean, there could be an app store, right? There could be an app store for you got your general purpose bot, and hey, if you want, but I think in order for the bot to
have your bot write apps.
Right? But if in order to have your bot perform a certain function, does the future bot dojo have to train it? And do you need a lot of examples of that? Do you need to do a lot of it in order to get good at it?
So neural network training and the state of AI, the way that it is right now, is probably not what it's going to look like in 10 years. The cars don't learn for themselves right now. Right. And it's going to be a while before we let the cars learn for themselves. And when they do look for themselves, they'll probably take what they learn and upload it to the cloud. So all the other, agents have that too. I mean, we do that after a fashion right now with Tesla's data engine, right?
Right.
Where they, they're basically learning collectively, and everything they learn is going into their memory. It is extremely likely that at some point we're going to start augmenting these neural networks with local storage, so that they have, right now neural networks effectively have this super long-term memory, which is their skills, their core skills, like being able to recognize a tree. And then they have this extremely short-term memory, which is what happened in the last 10 seconds. But we're not really giving them this intermediate memory, like, oh, I drove this route yesterday and I remember there was construction, so instead I'm going to go around. I'm going to go this other way, right? Or I've driven this street 4 or 5 times and I know my owner really hates this left turn, so I'm going to pick another route. So there's kind of an intermediate set of functions there. We will unquestionably give those capabilities to the thing. So in a sense, that's kind of this sort of composite skill. It's built on a lot of fundamental skills that have to be learned at the neural network level, but it's a composite skill, like, if you can make miso shiro, if you can make miso soup, maybe you can also do an omelet or whatever the deal is. I mean, the core capability of being able to go in the kitchen and use the implements that are in there is basically the same. So what it takes to add these additional kind of composite skills is a lower, it's a lot less. Once you've got a few of them, you've built the infrastructure for adding additional composite skills relatively easily. But there has to be the infrastructure in the robot to allow it to develop an individual skill that's necessary for some individual thing that it's doing. And we will do that eventually.
Does the robot effectively end up having a neural network training chip in it as well as an inference chip, so it can train itself?
Yeah, probably at some point.
I love your cooking analogy, by the way. It knows how to cut, it knows how to turn the stove on, it knows how to, but then it's like, well, what's the recipe? Right. And now it has to learn different recipes.
Well, no, actually,
that's a really good analogy.
What do is like ask Google, what's the recipe for a Manhattan?
Right.
I'd like it dry, please. Perfect.
Right. Okay. I am out of questions. Let me just see. I don't know. We've been going for a long time. I'm actually pretty tired. I don't know how you're feeling. Is there anything else
on your... other things I have to do, so.
Well, before we go, anything else that leaps out at you we haven't covered that, from AI that you're really excited about, or are you ready to wrap it up?
Man, I'm excited about so many things. It's hard to. I've got a couple people have asked me, like, what was the most, what struck you the most about it? And I have to say the ambition of it is probably the thing and then my impression, like, they're doing reinforcement learning for the planner in the FSD. Oh my God. Like, that is freaking awesome.
Are you talking
I'm
about
so excited about
the
that.
Parking lot thing?
No, well, it's okay. It's,
the little tether goes out with the little edges, and it figures out where it's going. Is that the one you're talking about?
Yeah, that's the Mu0 algorithm, right? They're using Monte Carlo tree search with a couple of neural networks in the loop to basically do the local evaluation, and they're training it, on real world examples. It's a reinforcement training technique, right? You give it you give it lots of parking lot dilemmas, and then it plays like an Atari video game, right? It's like, how do I get there in the smallest number of steps, or with the least amount of commute? So just like AlphaGo, it can sit there and play these games and gradually get better and better. That's reinforcement learning. And I think what was it? Jan LeCun, he's one of the godfathers. You know who he is, right? He said reinforcement learning is the cherry on top. And we do a lot of research with reinforcement learning because the potential there, when you get it working, is amazing. There's so many things you can do. Like, reinforcement learning is how you just put the reinforcement learning algorithm into your robot and it learns to operate the body. It learns the way a kid learns. Kids start, they're not tabula rasa. I mean, they've got a lot in them, but they learn everything that they need to do. And reinforcement learning is, in a sense, it's that core capability. And the fact that Tesla is using that already for the planning module in the car is freaking awesome, because when they get that working, well, it's like the space of possibilities really opens up.
That reminded me of something I wanted to ask you about. So they talked about simulation, and I did not see that coming. I did not think that was going to be a part of AI Day. and it was really compelling. And I literally did not realize it was a simulation when they first showed it and the Cybertruck was up ahead. I did not predict that. That looked real to me. Mm-hmm. So one of the things I saw on Twitter, and maybe it was in the news, were people saying, aha, Tesla's not really training on real world data. They're really training on simulations. Like, that's not how I took that.
I saw Stephen Mark Ryan's send up of Gordon Johnson's appearance on CNBC.
I didn't see that yet.
Yeah. Okay.
But the way I took that was, look, we're training on real world data, but there's probably other things they're doing with the simulation, but there are these rare cases, these edge cases that are so rare that we can't find more of them in the real world data. So we'll take the edge case we found and we'll put it in the simulation, and then they'll create a bunch of similar edge cases related to that and train on that. What are some other uses? Sorry.
Well, okay, you can test hypotheticals, right? Frequently, when you're at a capability, you have a hypothetical you want to test it against, and maybe you don't have the system ready to put in a car yet. And so you can build a hypothetical and test that. One of the things that I thought was, one of the most compelling cases is, say that you want to really drill down on some autopilot failure you had. You got a clip of some failure, and this is what they demonstrated. Here we have, we took this clip, we ran it through our auto labeler, it built a 3D scene, we pushed that into the simulator, we built it, and now we can run variations on it. So this is a thing that Waymo has talked about for a long time, about how they've got the ability to basically look at every scenario that the car sees and explore it in detail. And you can Monte Carlo it too. You can have the system just generate random variations on this situation that you had a problem. Like, is there an even worse, but adjacent bad situation that we need to know about? Or, now we build our fix and we run it. Let's try lots of slightly different situations that are very similar to where we had this problem, and see how the software performs. And you can close the loop on that, right? Which they talked about doing, where you challenge it with a bunch of random variations on something that is a problem. And if you've got a planning algorithm that's trying to figure this out, the planning algorithm gets better at that. And then you look at the places it was no good, and you automatically generate variations on those. And then the neural network automatically trains against you. Close the loop so that, the simulator is useful for all of that kind of stuff. The weakness of the simulator is that it's never going to have the distributional, it's never going to capture very well all the space of things that happens in the real world. It doesn't, they talked at length about how they look at the physics of the camera to try to get the vision. And, they're simulating diffraction of the diffraction of the heater wire and atmospheric effects and all these things. Because one thing we know about neural networks is, like, if there's a hole in the simulation, if there's a shortcut, they will find it. And the shortcut they find won't work in the real world because it's specific to your simulation, which is why simulation, it's basically a tautology in the machine learning world today, that if you train in simulation, it will not work in the real world. Right. You can get very narrow cases in simulation, very narrow cases in the real world, and you can do transfer learning, and you can use simulation to bootstrap your way into some basic level of functionality that you can then build on when you get to the real world. Simulation is really useful. It is not useful. It is a super important tool to have in the toolbox. It is not a substitute for real world data.
And do you think they're going to start selling their simulator for, like, video gaming?
I think they're building it on Unreal Engine. Probably they didn't mention it, but that's what it looked like to me, the rendering style and whatnot. Okay. That's what when he said, "Hey, here's our Cybertruck. Where do you think it is?" And I was like, "It's in Unreal." Okay. that was my answer to the TV when I heard it. And he's like, "Well, we built ourselves a simulator." And maybe they did build it from scratch, but I think they're probably built on top of a commercial rendering, environment. And it's probably Unreal, and so they can't license it because the core of it is already some piece of public domain code that they don't own.
I thought the guy said that they were planning to do that. That they could sell simulation as a service. That's what I thought I heard.
They can sell Dojo as a service. They can sell FSD as a service. Like, all that in theory can be done. As long as they have as long as their ambition exceeds their reach by the degree to which it seems to constantly do, I'm really skeptical that we're going to see them going into these incremental revenue adjacent markets.
All right, really quick, I just want to tell you, R2 and others in the chat are really I want you to know you're appreciated. I don't know if you realize how much you're appreciated. A lot of people, there's a lot of people watching, there's a lot of people appreciate you. So I want to thank you for coming on. I'm going to let you go, and I'm going to say goodbye to the audience after you're gone, if that's okay. I assume you have stuff to do. So, all right. So
I got to have a floor to fix. I've got to deal with.
So thank you very much for joining us, and I'm going to do a little bit of chat Q&A with the audience after you're gone.
Okay, cool.
Thanks very much.
Thanks for having me on. It was it's always fun.
All right, thanks.
Take care.
All right. So I'm here. Let's go to. Oh, that's not working. All right, we'll do it like that. So thanks everyone for watching. Let me see if there's any questions. I'm going to wrap up soon because I'm exhausted. But just want to see, do people have questions? Is there anything? Does Dojo have? James is gone, so if you have questions for me, I can try to answer them. But I felt like I had him on for too long, and I'm pretty beat because I've been going since. I think I'm close to 4 hours when you consider everything I've been doing. So all right. So I'm gonna wrap it up. I want to thank everybody for watching. I want to thank the Vasa law firm in Sweden and the Patreon supporters for helping this channel. Doing here. Hey, you can see the little light behind me. Yeah, I've been drinking these, Ben. I've been drinking these. This is the second bottle. I'm on the second bottle. So yeah, it's my bladder's okay though. So what do I think the first thing they'll want to teach the bot? They want to teach the bot to understand the environment around it. Oh, what is a small EV? So the joke is that I would start a small EV company that's going to be a small company that makes small EVs. So the small EV is a one-passenger electric vehicle. That's the idea. A one-passenger electric vehicle is designed for self-driving, so it has no steering wheel and no pedals from the get-go. And the hope is you build it, and by the time it's done, there's self-driving software out there that you can pay for to run your vehicle. So, all right, I'm gonna go. I want to thank everyone for your support and thank everyone for watching. And it's time to let this go. So I probably will be making a video shortly about Tesla Bot, a full video about Tesla Bot. I'll probably be making videos about simulation and Dojo and everything, edited videos. I believe I have an interview this week with Ricky from 2-Bit Da Vinci about universal basic income, the theory that if the robots take away work from humans, how are humans going to survive? And a popular answer from Andrew Yang and from Elon Musk is universal basic income. I think it's the wrong answer, so that's going to be an interesting conversation. And then I'm going to be doing the same conversation again a month later with a guy named Scott Santens, who is a big believer in universal basic income and sort of a leading figure in that field. But anyway, thank you to the moderators, Mark Plott, Mark Potocznik, Jim Whitehead. I don't see who else was there. Thank you to the channel members like Ben Pena. And thanks everyone for watching. I'm out.